All right. So second lecture is the second lecture of Yoshitaka Hatta.
All right. So yesterday I introduced the Jaffe-Manohara sum rule for the nucleon spin and explained the helicity components. So we have quark helicity delta sigma and gluon helicity delta G, and then explained how we can measure these quantities in experiments. But there are some loose ends to tie. So let me start with the rest of the Jaffe-Manohara sum rules, and that is the orbital angular momentum. So here's a quick explanation of why do we need orbital angular momentum. Why we cannot neglect this orbital angular momentum, and that is actually obvious from this de Graaff equation. So this so delta sigma, I write it in. So by delta sigma of x is basically the flavor singlet part of the polarized quark, polarized anti-quark distribution. And of course, they obey the polarized version of the de Graaff evolution equation. And then it mixes, because this is a flavor singlet, it mixes with the evolution equation for the gluon, polarized gluon PDF. And this is a de Graaff evolution, and we have kernels like this. So this quark component, this 1,1 component is actually the same as the polarized splitting functions, but the rest is different. But anyway, this has been derived by, I think it was derived by Parigi and Carré. So this is de Graaff equation, the polarized version, the one loop. And then I integrate over, so I can integrate both sides over x. And the integral of this is basically the delta sigma, the total helicity contribution by quarks to the nucleon spin, and the integral of delta G is by definition of the gluon helicity contribution to the proton. So I integrate over this relation over x on the left-hand side and right-hand side, and you immediately notice that this is not Q-square independent. So this guy evolves with the Q-square, which means that helicity is not a conserved quantities. Okay? Because helicity is only a part of the angular momentum, and the rest should be accounted for by the orbital angular momentum. So this is in equation. This is basically the statement that only the sum of helicity and orbital angular momentum is conserved. So if you only consider the first two terms, and you still have a Q-square dependence, the renormalization scale dependence. But if you add the quark and the gluon contribution, the orbital angular momentum should be Q-square independent. So, right. And in practice, in fact, the Q-square dependence of this delta sigma is actually very weak. It actually bunches at one loop, and it only starts at two loops. This was first result, very old result by Kodaira. So this is evolution equation for this is alpha squared. So this is a two-loop anomalous dimensions, and you can see alpha s over pi is 0.1, and you have 16 in the denominator, so which cancels this 12, and then you see this number is like 0.01. So it's very weak scale dependence. So if you plot this delta sigma as a function of renormalization scale, it's almost flat like this. So this is dependence of delta sigma on Q-square dependence of delta sigma, which is completely flat because this is very weak anomalous dimensions. However, delta G has a larger anomalous dimension, so it grows like this. So of course, it violates the spin sum rules. It has to be compensated. And in this case, it is compensated by the gluon, the orbital angular momentum of quark and gluon, which moves in the opposite direction, so that the sum of all these guys are always 1/2. And you can, it's not only the total helicity and the orbital angular momentum, but you can also look differentially in the X space. So you can define the Parton distribution function for the orbital angular momentum, and you can look at the x distribution, x dependence of these distributions. And you see, so this is the x-axis is a log 1/x. So if you go to the right, it's a small x region. And in the small x region, this delta G goes up. But this is compensated by the gluon orbital angular momentum density, which has the opposite sign, so that the sum is manageable. So this means that the orbital angular momentum is always there. You cannot, it might vanish at one particular value of Q, but if you go to the different scales, it will not vanish. So we want to think more about this, because there's been no measurement of orbital angular momentum whatsoever until as of now. All right, so let me come to the more basic question: what exactly is the orbital angular momentum? So yesterday I told you that Jaffe-Manhart decomposition, quark and gluon orbital angular momentum is not gauge invariant, but one can actually promote it to a gauge invariant form. And there's been lots of controversy over this around like 2008, 2009, which was triggered by this paper by the Chinese group, Chen et al. And this created a lot of confusion and debate and fights within the community. But I think the dust has settled, and this is the end result. Okay, so this is a gluon helicity. It's a gauge invariant version of the gluon helicity. So take the matrix element between the polarized proton state, and you pick up the coefficient of S class, that's delta G. This is a gauge invariant definition of polarized gluons. And you can do the same thing. This is a quark orbital angular momentum, the canonical orbital angular momentum, which is, instead of the partial derivative here, I have something called d pure, what I call the d pure, which is defined like this. Okay, so in d pure, I have to define a physical, and a physical is like this. Okay, and this is for the gluon orbital angular momentum. So I have again the d pure, and instead of A, I have a physical, and a physical is defined like this. So I cannot tell you all the stories which led to this result, but you can just follow it. And I will motivate you why we get this derivative like this in the next slides. So I think this is the final answer. It's a gauge invariant completion of Jaffe-Manhart decomposition. All right, so let me explain why do I get this weird expression like d pure, which has involved the Wilson line and the field strength tensor. So in order to explain that, I think it's the best starting point would be the Wigner distribution, because orbital angular momentum can be defined through the Wigner distribution in QCD. So let me remind you what is the Wigner distribution in quantum mechanics. So it's kind of a bit of a digression, but it might be still useful. So let's go back to the quantum mechanics, and of course, position and the coordinates. You cannot define it simultaneously, but still, nevertheless, you can define this kind of phase space distribution function in quantum mechanics, and it's defined like this. So if you have a quantum state psi and position space eigenstate, and then you find take the Fourier transform with respect to the relative coordinates, and then this associated momentum P, then you can define the joint distribution in position and momentum. That is the Wigner distribution function. And the nice property is that if you integrate over the position, then you get the momentum distribution. And if you integrate over the momentum, then you get the position distribution function. But so this is very nice, but of course in quantum mechanics, we have uncertainty principle, which means that this cannot be really a probability distribution score, which means that it can becomes negative. So this is a Wigner function for the harmonic oscillator in 1 dimension. So the phase space is 2 dimensions, so you can calculate this Wigner distribution. And this is a ground state harmonic oscillator, which is fine. So this is a position and momentum in 2 dimensions. But already starting from the first excited state of harmonic oscillator, you get this sharp negative peak and goes like this. So this is a Wigner distribution in quantum mechanics. Now, you can do the same thing for the QCD. You can define a similar object in QCD. It's a Wigner distribution defined like this. So this is a quark Wigner distribution, which is a function of transverse coordinates, k perp. So this is a 2-dimensional vector, and it's also a function of p perp, is the position space. So this is a 5-dimensional object, which is sometimes refers to. That's why people sometimes talk about the 5-dimensional tomography in the context of EIC. And in a sense, this is a model distribution in the sense that if you integrate over position and momentum, just like before, then you can successfully reproduce all the known lower dimensional pattern distribution functions. So if you integrate by B perp, you get a TMD, and if you integrate by K perp, you get GPD, and then so on, like this. Yes.
The B perp in GPD is the impact parameter technically with the BA columns.
B perp is actually conjugate to the momentum transfer. So if you have an exclusive, like elastic scattering,
Yes.
proton goes to proton, and there's this momentum transfer.
Yeah, I understand GPD the concept, but I
Yeah.
think in the context of a collision, if we had, it will be the same as an impact parameter.
Yeah, impact parameter, yes, it's the same as impact. All right, so this is a Wigner distribution function introduced in this field like 20 years ago. So, and this is a very useful object to talk about the orbital angular momentum, because it's very natural to define orbital angular momentum in this way using this phase-space distribution, and which is very intuitive. So it's just B cross K. It's a classic definition of the orbital angular momentum, weighted by this Wigner distribution function. So this is a very natural way to define the orbital angular momentum. And as long as this Wigner distribution is gauge invariant, the resulting orbital angular momentum is also gauge invariant, almost by construction. So so this is a basic definition. And then if you look at this Wigner distribution in details, then you will find a part that depends on the spin like this. So this has many terms in it, but we pick up one particular term in this Wigner distribution function that looks like this. There is a term like this. If the spin is proton is polarized, then there must be a term like this. And then so I just plug it into here and then find this expression that the quark and gluon orbital angular momentum is given by the second moment of this this coefficient function here. So if you find a term like this, then that will give you the orbital angular momentum. And as I told you, the OAM is always there. It must be there. So there must be a term like this. And then from that, you can define the orbital angular momentum. And so let's look at this calculation in a bit more detail. So as I told you, I have to first make the Wigner distribution function gauge invariant. And I do it in the following way. So it's a non-local, it's a bilocal spinor product. So you have a spinor antiquark in one coordinate, the other coordinate. So I have 2 points in this plane, and I attach a Wilson line, which is called a staple-shaped Wilson line, like this. So I start from this point that goes to the minus direction along the light cone to infinity. You have to go to the infinity there, and then comes back. Okay. And so there is a transverse Wilson line here, and then there is a light-like Wilson line. So this what I call the staple Wilson lines. So this is my gauge invariant Wigner distribution, and I plug this function into the definition of this orbital angular momentum, and I'm going to show you that what you get here is this funny object dpure, which I defined in 2 slides ago. So that's the statement. So here's a proof. So first, what you do is so I have this K perp here, but I can replace this K pop with the Z pop derivative because I have this phase factor here, right? So K pop can be a derivative of this exponential factor with respect to Z pop, and I can do the partial integration in Z pop, and this derivative acts on this matrix element of. So I have to consider the Z pop, Z derivative of this object. And when you calculate this Z pop derivative of this with respect to Z pop, I have to differentiate this Wilson line, the stable shaped Wilson line. And that's a bit tricky part, which I'm going to work out step by steps. So I need to calculate this the product, the derivative of the Wilson line like this. So times this Coke field. And then, so I have a term which the derivative acts on this Coke field. And then there's another term where the derivative acts on the Wilson line. And this is a bit tricky. So this is a Wilson line extending from Z minus to infinity. And this is a formula. So this is a exponential over A plus. It's a path order exponential over A plus. So if you take the derivative, you get something like this. So A plus is differentiated at any point in the minus direction. So you have to integrate over this minus direction from Z minus to infinity. Now, so this is the first step. And the next step is that I replace this part like this one. So I think this is the trivial point that so F plus I is A plus. Right, so I can write this as D plus AI minus. Okay, so I combined these two terms into the covariant derivative, and then I kept this as it is. So I can write this the derivative of A plus as the difference between this and that. So what I did here is just a trivial rewriting. Okay. Now I keep this F plus I as it is, but this I do some manipulation of this D plus AI. And here's the formula. So I need to evaluate the integral like this, but you can actually write it in terms of a total derivative. So try to convince yourself that why this is correct. Okay. Well, just quickly, because so this x minus derivative acts on the end point of this Wilson line and also this Wilson line. So you get the commutator between A minus, A plus, AI. So you have A minus coming down from this first Wilson line. So you have A plus AI and you have AI A plus. So you get a commutator of between these two, which is a part of this covariant derivative. So you can write it like this, and then because this is a total derivative, I can do the partial integration and you just pick up the boundary values. Okay. Now I have the transverse gauge potential at the infinity, but this actually cancels with the one that you get by differentiating this transverse Wilson line at infinity. So this term I can throw it out. But the second term I just have to keep it. So I have to combine this term and this X plus I term, and I get this is a result. And this longer derivative, D pop plus the integral of this field strength tensor is what I call the D pure, the previous term. So this is the origin of this strange covariant derivative, and that would ultimately gives you the gauge invariant version of the orbital angular momentum that I showed you here. And you can do the similar thing for the gluon orbital angular momentum. So that's the origin of this funny expression. But this is how it is. So this is tied to the Wilson line in the light-like direction, this stable shape Wilson line. So I think this is okay. So this is the final result for the Jaffe-Manhart. So Jaffe-Manhart is gauge invariant. You can make it gauge invariant this way. All right. So that's okay. So let me come to the second loose end that I left yesterday. So the another problem of the Jaffe-Manhart decomposition is that the associated energy momentum tensor is not symmetric and not gauge invariant. But one can actually improve that in a different way from what I just explained. And that is called the improved energy momentum tensor, or it's called the Bell-Infante energy momentum tensor. So here's what I derived yesterday using the canonical procedure by using the Noether's theorem. By doing Lorentz transformation, I get this angular momentum tensor the usual way, which is not symmetric and it's not conserved. So the energy momentum tensor T canonical is not symmetric but not gauge invariant. However, there is a clever trick that you can always make this, you can always improve this by adding the something sometimes called the superpotential. So basically you add to this the canonical energy momentum tensor the total derivative of something. And you can always do that because when you consider the total energy and total momentum, this total derivative terms always vanishes when you integrate with space. Right? So you can always do that. And if you choose this capital G very cleverly, and then you can make this new energy momentum tensor gauge invariant and symmetric. So this is called the improvement, Bell-Infante energy momentum tensor. And the choice that you have to make here is given by this expression, where H is it's a reminder here. Okay, so I showed you the expression of H in my previous slide, and use that H and then construct this G tensor, which are 3 indices and plug it here. And this is guaranteed to work. If you do this, then you get this. The resulting T tilde is symmetric and conserved in both indices. And this, I leave it to you as an exercise. I think this is interesting. It's guaranteed to work. Okay, and the hint is that I'll give you a hint. So you just use this. So this canonical energy momentum, angular momentum tensor is conserved. So you take the derivative of this to 0, then that gives you some relation between H and T canonical. So you use that relation, and then you should be able to show that this is conserved. And in the case of QCD, so this is for generic systems. It's not necessarily in QCD. It always works. But in the particular case of QCD, what you get for T mu nu is this one. Okay, so that's another exercise. Okay, and this brackets in mu nu index. This bracket is a symmetric product defined like this. And so this is a T tilde, and this is an improved energy momentum tensor, and this is an improved angular momentum tensor. Okay. So I think this is a very instructive exercise, which is well, the first one is it's simple, I think, but the second one is a bit tricky, and so I give you another hint. In the case of QCD, you can use the following identity, which I think is useful in the broader context. But it just follows from the Dirac equation. So this fermion, the Koch field has to satisfy the Dirac equation, and so you write the 0 in this way. Okay, so you consider this particular product of bilinear, and this is first term is 0 because of the Dirac equation. The second term is 0 because of the Dirac equation. And but in any case, I take these linear combinations. And then I do some trick, manipulate this gamma matrix product. So you have a product of 3 gamma matrices. It's the same formula that I showed you yesterday. Yeah, so yes, and you can use this formula for the first time and the second term, and then you get this identity. It just follows from the Dirac equation. I think this is a useful formula, not just in this context, but in more general. So this is a very useful identity, and you will need this when you solve this exercise. Okay. All right, so this is called the Bell-Infante energy momentum. So now we have a symmetric and gauge invariant energy momentum tensor for QCD. You can arrive it from the canonical energy momentum tensor in this way. But you might think that this is very complicated, and some clever people can do it much better, much faster, and they can actually do that from general relativity. If you do the trick from general relativity, so it's very well known that in general relativity you can derive the energy momentum tensor just by varying the action, the gravitational action in the presence of gravitational fields. And so if you do that, then you almost immediately get this energy momentum tensor. You don't have to go through all this complication. It's very quick, but you have to be careful in the okay, so here's the procedure. So you start with the QCD Lagrangian in flat space, which is a four-dimensional integral of some Lagrangian density, and you embed this Lagrangian into the curved space. So the metric is not trivial anymore. So you have a non-trivial matrix, determinant of this matrix, and you have a G mu nu. So G mu nu is not anymore 1 minus 1. So, and starting from this generalized action in the curved space, you get this Bell-Infante energy momentum tensor immediately just by varying with respect to this matrix. This is a textbook. If you read the general relativity textbook, this is what it is. Okay, so but you have to be careful about the sign. For example, in most textbooks of general relativity, they use opposite metrics. So they often use a -1, +1, +1, +1 metrics. Many textbooks do that, which is opposite from QCD. And you also have to be careful about the sign difference. This is a technical point. So you might naively think that if you raise these indices up, then this G mu nu these indices just go down. But in fact, there is an interesting minus sign here. So I leave it to you as an exercise why you have this minus sign here. Okay. You need a bit of knowledge of the general relativity. And so that's the first thing to know. So beware about the signs. And another caveat here is that you might naively, so you have this fermion action, the clock action, which is contracted with the gamma matrices, and you might naively promote it to the curved space like this one. Okay, and you take a derivative with respect to this G mu nu following this formula, and then you make a mistake. Okay, this is wrong. Okay, so think about why it's wrong. It looks very natural, right? But if you do this, you make a mistake by a factor of 2, because there is a factor of 2 here. Why is this wrong? Anybody has an idea? Okay, so the reason is because this gamma matrix. So what is gamma matrix in the curved space? So gamma matrix is in the flat space. This is defined by the G mu nu, right? This is 1 minus 1 minus 1 minus 1. But if you go to the curved space, well, this you need some x dependence, right? So you cannot naively you cannot do this because this gamma matrix depends on x, depends on the metric by definition in curved space. So what you people do is usually introduce something called the Villebain. Yeah, so when you think about the fermion in the curved space, you need something like this. And that takes care of this X dependence of this curved matrix. So that's a small caveat. So this is, you can easily make a mistake like this, but you have to be careful when you take the derivative. But once everything is done correctly, then from this procedure, you get this expression immediately. So it's just one line derivation. So you can do it in two ways, from this general relativity method, or you can also do this lengthy procedure starting from the canonical and then do the improvement according to this Belling-Fante method. All right, so now we have a symmetric and gauge invariant energy momentum tensor. So then we can talk about the spin sum rule in a different way. That is called the G decomposition, which is a different way of decompose the proton spin. It's a different decomposition, so that each element has a different values. And this decomposition, which is proposed by Shandong-Ji, I think it's 95, is based on this Belling-Fante energy momentum tensor. So here's the definition. So you're not working in a light cone anymore. So you can even go to the rest frame of the proton and just look at think about, so the proton spin is pointing in the z direction, and just compute this Jz of the quark and gluons by computing this matrix element. And here, what you use here is the Belling-Fante energy momentum tensor. Maybe I should put a tilde here, but it's the same as what I showed you before. Now, so basically you want to calculate this matrix element, but to evaluate this, what you do is the following. So this is a forward matrix element. The proton momentum here and here is the same, but first you generalize to the off-forward matrix element. So I have a slight difference. I do introduce a slight difference in the final state momentum. So P prime is slightly different from P, and then take the limit of P prime going to P. Okay, it's the same thing, right? Now I use this operator identity. So this is always true. So any operator evaluated at coordinate X, you can translate this operator to the origin of the coordinates up to this exponential of the momentum operator P hat times X. Okay, so you can do this trick for any operator, and then this momentum operator acts on the P and P prime, and what you get is a difference between P minus and P plus, because you have a plus sign and minus sign here. So you get the exponential of delta of X, and then is it obvious here? Oh, okay, so what could you? So I have something like I delta I xi x different x t 0j like this. Okay, because I want to take care of this factor of xi, which is explicit in the angular momentum tensor. So I want to get rid of this xi, and the way we do this is to write this as a derivative with respect to its momentum transfer. Okay, then I can get rid of this xi. Then I do the partial integration in Ex. Wait a minute, doing something wrong. No, it's fine. It's fine. Okay, so I have this derivative with respect to delta I. Then, so there is no X dependence, and then I take the delta going to 0. So this exponential disappears, and then what I get is this local matrix element. So you compute the forward matrix element and take a derivative with respect to delta and set the delta equal to 0. Okay, so this is how you're going to calculate this matrix element, because because there's explicit factor of xi, and that makes things complicated. So you want to get rid of that. So basically, you replace this xi with the derivative with respect to the delta. So I need this expression, this upward matrix element of the very infant energy momentum tensor, and this matrix element is known as the gravitational form factor. So this is the first encounter with the gravitational form factor, which I'm going to talk about at length tomorrow. So here's the most general parameterization of this upward matrix element, quark and gluon. I'm showing only the quark part. And you need a 4 form factor, A and B and D and C bar, and take the matrix, take the derivative of this spinor product with respect to this delta I. And so you see, for example, this term, you have this term is quadratic in delta, so this term doesn't contribute because you take only one derivative and set delta equals to 0. So this term doesn't contribute. And then this term doesn't contribute because you have a G alpha beta, but I'm looking at this off-diagonal component, so this term doesn't contribute. But this B term, this contributes because there is one factor of delta here, and so this term survives. And in fact, the first term also survives. And that is not obvious, but if this delta dependence actually comes from the spinor product, so you have the U bar, gamma alpha U, and if you consider the small delta limit of the spinor product, you find a term which is linear in delta. So you have to take that into account. So you get a contribution from this A term and B term, and that's basically the G sum group. So the proton spin 1/2 can be decomposed into the quark part and the gluon part, and the quark part and gluon part are related to this AP gravitational form factor. Okay, so that's the G sum, which is different from, obviously different from Jaffe-Manoha. And so I think, well, probably some of you already know that this A actually is nothing but the momentum fraction of proton carried by the quark. So this is the second moment of PDF. Okay, upwise PDF. So they sum up to 1 because of the momentum conservation. And this means that so when you sum over quark and gluon, this A term sum up to 1, and there is 1/2, which matches the 1/2 on the left-hand side, and that means that the sum of B over all flavors and quark and gluons must be 0. So this is a consequence of angular momentum conservation. Okay, so this is a very general constraint on this gravitational form factor. A and B has to satisfy this sum. Now, so this is at this point, I haven't made any distinction between helicity and the orbital angular momentum. This J is the total angular momentum of quark and gluons. Okay, but in the case of quarks, you can do the further decomposition into the orbital angular momentum and helicity, and well, you can do that by using this operator derivation. I think this is what this is. This you can also derive this using the identity that I showed you here. So use this relation, and then you can derive this equation, and then you plug it into the definition of JQ, and you find that this quark part can be further decomposed into the helicity part, which is actually identical to the Jaffe-Manoha decomposition, plus the so-called kinetic OAM. It's different from the canonical OAM that I showed you before. It's it's numerically different. And this OAM features the covariant derivative. So it's like, so it's manifestly gauge invariant, and it's local operators. So the advantage of this decomposition is that all the operators involved are local and gauge invariant. And so so that means that they are calculable in Lattice QCD, and there's always already been a calculation of that. I think Martha has lecturer in the afternoon. I think she might have calculated this. All right, so you might be wondering what would be the quantitative difference between the canonical OAM and kinetic OAM. So there are two different things, and you can explain the difference in terms of the Wigner distribution again. So previously, I took a roundabout route going from here to there. I took this staple-shaped Wilson line, so fast going to infinity and come back. And that defines a canonical orbital angular momentum. But some people may ask, why not just go directly from here to there? And if you do that, then what you get is this covariant G's orbital angular momentum. Okay, so the difference between these two is actually the this closed Wilson loop in this infinite length Wilson loop. You get some extra torque as the quark travels along the light cone and comes back. And that explains the difference. And you can actually see this difference numerically in the lattice QCD, which was done by Michael Engelhardt in 2017. So what is shown here is the orbital angular momentum as a function of the length of this light-like Wilson loop. Okay. Well, you should take it as a grain of salt because there's no light-like direction on the lattice, so you have to do a lot of tricks. And I don't think this is the final result, but I think this is the first attempt of this kind. And so since this is a length, so 0 means that you go from here to there just by a straight line. And so this is a kinetic orbital angular momentum. And so the canonical orbital angular momentum corresponds to the infinite length. So you go to you extrapolate to the infinite length, and then so this asymptotic value is the canonical. And you see the numerical difference between the two definitions of the orbital angular momentum. And that comes from this extra closed loop in the light line directions. So that's basically the yeah, so that's basically the end of the spin part. If you have questions, I can take it at this point.
Is there can you maybe give me a physical interpretation of the different ways to close the loop?
Yeah, that's a very good question. I suggest you look at the paper by Matthias Burkhardt, which was written in 2012, I think. So he has a very nice physical interpretation. So the difference is this. So the difference is this field strength tensor, F plus I. And you have this, you have a nice physical interpretation. So this F plus I is actually, if you write it in terms of the electric field and magnetic field, you can write it like this. Okay. So field strength tensor, you have an electric field and magnetic field. And this particular component F plus I can be written like this. And this is nothing but the Lorentz force. So what is shown here is that so this angular momentum is basically the x cross Lorentz force. So as the quark travels to the infinity, so this is basically the torque. So as the quark travels to the light cone infinity, it receives a torque from the rest of the systems, and that adds up to the angular momentum tensor. So this is a physical interpretation by Matthias Burkhardt about this difference between the two types of momentum. That's maybe I should have coded here, but somehow I missed it. All right, so that's so much. That's it for the spin. And then the rest of my talk today, I'm going to talk about the generalized pattern distribution. And I have only 15 minutes.
15 minutes.
So GPD is a very vast subject, and I'm going to give you a review in 15 minutes. But if you're interested in, then there are very famous reviews. There are two famous reviews by Max Steele, Beletsky, and Radulsky. So you're encouraged to look at this. These are like 200, 300 pages reviews. So it's a very vast subject, and so there's been a lot of activities in the EIC community. So let me give you a brief recap of this. So here's a definition of GPD. This is unpolarized GPD and polarized GPD. So the difference from the PDF is that the initial momentum and the final momentum are different. That's the only difference. But this small difference actually makes a big difference. So first, this matrix element has two terms. So in the case of PDF, I have only one term, which is called PDF. But in the case of GPD, you have two terms. The second term has explicit factor of delta, which is a momentum transfer. So of course, this term vanishes in the forward limit, but at the non-forward limit, you have this extra term GPDE. So we have GPDH and GPDE. And in the case of polarized, you have a different Lorentz different gamma matrix structure. You have H tilde and E tilde, and H tilde reduces to the polarized Cook distribution in the forward limit, but the tilde doesn't. So this is entirely new. There's no collinear, there's no forward analog of that. And also this PDF depends on extra variables. One is it's called the skewness, eta, which is defined like this. So this is a momentum transfer in the plus direction divided by the full momentum plus P plus of the initial state. And if you look at the literature, then different definition of skewness exists. So you should be careful about which. And all these different definitions, they differ by power suppressed correction. So. And also, it also depends, so there's a dependence on the skewness, and also there is a dependence on T, the momentum transfer, which is delta squared. And I leave it to you on an exercise that derive this formula. T can be written in terms of the mass of the proton and skewness, defined like this. And then there's a transverse component of the momentum transfer. Okay? It's non-trivial. So try. All right, so then the good thing about this GPD is that it gives you an intuitive picture of how the patterns are distributed in the impact parameter space. So to see that, set skewness equal to 0, and then GPD depends on the transverse components of the delta, the momentum transfer. You do the two-dimensional Fourier transform to go to the impact parameter space B. So you start from the GPD in momentum space and go to the pattern distribution function in the coordinate space. So you can, I think this is, I don't know, I forgot if this is a model calculation or maybe it's an extraction from the data. You can see as a function of X here, so this is X. So pattern with the given momentum fraction, how the patterns are distributed in the impact parameter space. So if you go to the small x, then patterns are more widely distributed. The large x is more narrowly distributed. So you can get this intuitive picture of the hadron coordinate space. And you might think that you always get a spherically or symmetric distribution because this GPD only depends on T, which only depends on the magnitude of this momentum transfer. But the interesting thing happens when the proton is polarized in the transverse direction. So if the proton is polarized in the transverse direction, the second term comes into play, and so you have this spinor product U bar and sigma plus nu and U. So this spinor product actually depends on it's approximately given by this expression, and this S is the transverse spin of the proton. So I get this linear combination in the small t region. It's a combination of H and E, and you have this explicit dependence on this delta. And if you do the Fourier transform, go to the B space, then because of this delta factor here, you get a distortion of the density in the impact parameter space. So you have actual. So it's a cross product between spin of the proton, which let's say in the x direction, and you have a y direction, so a derivative with respect to the by, and that gives you a So the distribution in impact parameter space is distorted because of this GPDE, which is again the work by Matthias Brook, 2002. All right, so one can also make a connection to the gravitational form factor. So here's a relation. So if you take the second moment of GPD, so you first multiply by x and then integrate over x. Okay, and then if you do that, you get this matrix element of this local operator, and this is nothing but the t plus plus of the quark energy momentum tensor in the Bellin-Fante form. And this matrix element can be parameterized by the gravitational form factor that I introduced before. So I just pick up the plus plus component from there, and this is a result. And so that means that this A and B form factors are given by the second moment of the GPD, H and E respectively. So that means that you can write the G summary in a different way using the second moment of the GPDs. That's a different version of the G summary. It's the same formula, but just written in a different way. Previously, I wrote it as a B and A and B, but I can express it as a second moment of GPDH and GPDE. All right, so to have time. So how do we measure the GPDs? You can actually measure the GPD in experiments, but that's very complicated. And the usual way is to use so-called the deeply virtual compton scattering, DVCS, or deeply virtual meson production, DVMP. And these are exclusive processes. So in the final state, you only have limited number of particles. You catch all the particles in the final state, but there are only a few particles in the final state. And typically you select the photon or ion, rho meson, and omega mesons. And all these are called exclusive processes. It's a very rare event. So the cross-section is very small compared to the inclusive processes. So that means that we need high luminosity, like at the JLab and the EIC. So only these places has a potential to measure this process and extract the GPDs. And so here's some kinematical, which you can just look at. So I have, so this photon is a virtual, but this final state particle can also be virtual or has some mass. In the case of photon, it's massless, but in the case of vector meson, the final state also has a virtuality. So I define Q1 and Q2, which has Q1 squared. Okay, so I have Q and P and the momentum transfer Q. Q is basically the square of this one, and the momentum transfer is delta. In this case, I have a usual Bjorken variable, X Bjorken, and I have something called the generalized Bjorken variable, which is defined in terms of the average P, average Q, and average Q squared. And I also have a skewness that I introduced before. So here's an exercise. Starting from this definition, show that in the case of DVCS, when this photon is massless, you have this approximate relation. Skewness is approximately equal to the generalized Bjorken variable, and we just related to the usual Bjorken variable in this particular relation. It's not trivial, but it's just a kinematics. All right, so let me show you the derivation of the Compton amplitude. So, so that's basically the end of my lecture. So, so the scattering. So I want to compute this scattering amplitude here, and want to try to make a connection to the GPD. And I'm showing you a derivation right now. So, so this is, you have photon here, and you have photon. Let's say in DVCS, you have a photon. So you have two photons. So it's a correlation function of a current, electromagnetic current operator. So it's very similar to the structure function in DIS. The only difference is that the final state and the initial states has different momentum. This is exclusive. This is amplitude. It's not a cross section. So this is a Compton amplitude, and I want to analyze this using a perturbative QCD. And the way you do it is, again, we do the operator product expansion. So suppose this Q is very large, so this correlation function is dominated by the small y region. So I can do the OPE. And this time I'm doing it in the coordinate space. That's convenient. So this contraction between clock fermionic field is basically the free fermion propagator. This is a fermion propagator in the coordinate space. If you're not familiar with this, you're familiar with the momentum space propagator, but this is a propagator in the coordinate space. Okay. Now I have a product of 3 gamma matrices. So I have gamma mu here, and I have gamma from here, and I have gamma from here. So again, I do the decomposition of this 3 gamma matrices in terms of the symmetric part and the anti-symmetric part here. Okay. And I have an exponential factor here. So there are 2 terms because I have 2 ways of contracting the clock field here and here. Okay, so now I have a matrix element of psi bar, psi, and this gamma matrix here, which I write it in this way. So this is, I do the integrate, I go to the, yeah, okay, so this is just a trivial identity that you can write this matrix element in this way, and this is nothing but the GPD. Okay. By definition, this is GPD, which is sum over this tau. There is a summation over tau, but I only pick up the twist 2 component, which means that tau is plus, okay, and discard the other components. That will be a higher twist effect. Okay. Then I think the rest is well, the rest is also complicated. So I can do the y integration here. Now I have d for phi, d for y, and I have an exponential of this y, and I have y from here. But this can be done. You can do it. Then what you get is expression like this, and then you work out. So expand the denominator here, and then you remember the definition of generalized Broken variable here, and also the x. I think at this point, x is a dummy variable. This is not the Broken x. It's just an integration. It's a dummy integration variable here that I introduced in this step. And then you obtain this expression. So that's the derivation. So this is a Compton form factor, a leading order Compton form factor, T mu nu, just scattering amplitude of DVCS. You have 2 contributions. One is coming from the unpolarized GPD, and the second line is coming from the polarized GPDs. So this is a complete derivation of this leading order formula, which is derived in the 90s. And so this was well, probably you will see an expression like this. So this is a famous kernel of the Compton form factor. You will see if you attend the talk of DVCS GPD, everybody basically shows this formula. And here's the derivation. Okay, so this is just a leading order, but the current state of the art is the next leading order calculation. And this was done last year. No, sorry, it's not last year, but a few years ago. And Jakob will show in there, but he's supposed to cut program. He's working with me. All right, so that's the Compton. Okay, so this is just a leading order, but if you go to the higher order and if you try to make a connection to phenomenology, then lots of things happens. And so that's why GPD field is so rich and so complicated, and there are lots of activities in the EIC communities. It's very difficult. GPD is a very difficult object to deal with. And first of all, there are more variables. For PDF, you just have X, right? But GPD, you have this skewness eta, and also this momentum transfer T. And so there's, if you want to extract functions with more variable, that's more difficult. And obviously, it's more difficult. And also, there are more GPDs. So already at this unpolarized GPD, there are 2. So there are 2 GPD. So in PDF, you only have 1, but the GPD, you only have 2. You have 2. So the number of pattern dispersion is basically doubled. So that also makes life complicated. And also, as you can see here, this compton amplitude, both unpolarized GPD and polarized GPD contributes. Okay, so even if you do the unpolarized scattering, polarized GPD contributes. So that's very different. So it's very even in unpolarized scattering, you get contamination from the polarized GPD. So that's another complication. And also there is a severe inverse problem. So this is what you get from experiment. This is the compton amplitude. And this is, you can see this is integrated by x from -1 to 1. So if you suppose you extract this from experiments, okay, how do you reconstruct this function? Because x is already integrated. And so it's very difficult to do the decomposition of this integration. And this is completely different from the PDF case, because I told you yesterday that if you consider the G1 structure function of the function of x, and it's given by this polarized Cook distribution evaluated at the same value of x, right? And this x you can measure. So if you measure in G1 from experiments, you get x dependence of the polarized PDF immediately, at least in this leading order formula. But the situation is completely different in case of GPD, because what you can get from experiment is already integrated over x from -1 to 1. So it's very hard to reconstruct this GPD from experiments. And there are ideas to get around this in the community, but I don't have time to show you. And also another complication is evolution equation is complicated. So in the case of PDF, you just have this degraph equation, which is complicated, but it's manageable. But in the case of GPD, evolution equation is much more complicated. I don't want to show you. Even the leading order evolution is complicated. And also, it's difficult to access the gluon GPD, which is important if you want to test the G-sum rule. That's also included the gluon sector. It's very difficult to access the gluon GPD in experiments, but there are ideas. For example, this exclusive production of J psi in single spin asymmetry. So this proton is transversely polarized, and then you measure the left-right asymmetry of this J psi in the final state, and this process is sensitive to the GPDE of the gluons. I told you the connection between the transverse polarization and the GPDE, and that's another manifestation of this connection. So if you have transverse spin, you can access the GPDE. And since this is J psi, you can access the gluon part of the GPDE. All right, so there are lots of challenges. You must feel that might be pessimistic, but I think there are lots of activities in the research, many progress also in the largest QCD. People nowadays computing a GPD from the largest QCD, and I think we still have 10 years until EIC, so we many more progress going ahead. No, thank you very much. That's
hearing this program, let me just say a couple of words. Can I just say a couple of words? I see you. Preparing this program, we thought about placing the lectures, and I just want you to realize that we are doing this not because it is easy, just because we thought it was easy. It is hard, and the community realized that actually the program of extracting GPT is quite complicated. Department of Energy has funded topical collaboration, which is called tomography collaboration. I'm a co-PI of this collaboration. Our PI is actually coming here, and she'll be here in 20 minutes. She'll give a talk after lunch. Marta Constantino, she is leading the effort of extracting those distributions on lattice, actually calculating them, while I'm involved in the phenological program of extracting those from the data. Just to throw at you one more complication. If you look at this integral here, you can imagine a function h, which would give you a contribution which would be exactly 0, while h is not 0. And our colleagues from France figured this out, and they actually demonstrated that any order such a function can be constructed. so that you have a GPD that doesn't give a contribution to your cross section. And they call it a shadow GPD. Means that if you have your DVCS cross section, then you will always have this ambiguity up to those that are called shadow GPDs. We tried to solve this problem a few years back, and I think we know how to deal with those. With that, go ahead, and I'm sorry if that's.
You were just talking about how the polarized GPD contributes to the unpolarized. I was wondering if it goes the other way. Does the
the polarized DVCS.
yeah.
Yes, I think I think you're right. It also contributes. The unpolarized GPD contributes to polarized DVCS. I think. I'm not 100% sure, but that's my first guess.
Maybe it's too difficult, completely mathematical, but in this integral here, I see that if the H function is an exponential, this can give you something that has no integral and has a theta function between x and psi. And what that would mean, that have a step function that x is bigger than skewness. I can write it in the board.
So you're talking about so h of x and xi be a step function,
Be an exponential
exponential.
of I x minus parentheses x minus psi of t.
of t.
Yes, something like this.
Okay. No, h is a real function.
Okay, okay.
So you cannot have I here, but so
Yeah, I'm sorry, my propaganda, I have on brainwashed to find
Comments? Yoshitaka is joining us tonight, so we have a relaxed discussion of difficulties, maybe trying to solve some of the difficulties. With that, let's thank Yoshitaka once again. It's lunchtime. Start again at 1. Sound good? Let's start again at 1. So Martha is actually arriving at 12. Okay. Should be good. Yes.